Alright, we're doing question 6 on paper 6.1, sorry, of 0654 in winter 2017. Okay, we were measuring acceleration due to gravity of a small ball. Okay, we're shown the ball at the 0 centimeter mark, and I think later on we're asked to draw this ball. Okay, I might just label the ball at the 60 centimeter mark. Okay, okay, that comes a little bit later, I think. Yes, it does. Sorry, I got my questions mixed up there. Alright. First things first, you're asked to calculate, you're meant to draw the ball to show its position. That's the one, right? Okay, again, easily missed. It's 1 mark for drawing a ball to show its position after 60 centimeters. And when I first saw this, I thought there was a bit of a trick. Okay, maybe, for example, it began at 0, began at 20, and so therefore traveling 60 centimeters would actually bring it to 80. But no, we're beginning at 0, and we're going to 60. That is it. Okay, drawing a ball. You'll be very sad if we missed that mark. You're asked to calculate the average time, and you're being asked to give to a certain number of significant figures. Okay. It's quite interesting because they do talk a little bit about why we do this now. 2 significant figures. Well, all we have to do is add the numbers up, divide by the number of terms, in this case 3, you get 0.66, which to 2 significant figures is 0.87. Okay? The reason we do this, one reason that people give, is that the original data was 0.2, it was 2 significant figures, so there's no reason for the average to be different. Okay, and I put a little asterisk here. Okay, some people disagree with this. Actually, Cambridge itself disagrees with that sometimes, but that's only later when we get to A-level, and I don't think you guys need to worry about that so much. Okay, let's go on to question B. Okay, we record the value of that we just calculated into our table. We're being asked to calculate and record in the table the value of t squared. Okay, and again, I would follow the conventions being used in the other data points. You've noticed you've gone 1.37 squared to 1.88. Okay, 2 decimal places. Let's give all of our answers to 2 decimal places. That means with some of them it's not hard. 1.1 squared will give you a nice 2 decimal place answer, but these ones need to be rounded. Okay, why is that important? Well, you're going to be plotting a graph down the bottom. Okay. And there's a lot of work for us to be doing here. Notice they've been very nice to you. They've done the axes for you. I think the reason they've done that is because it's quite an awkward one. I've not seen many graphs that start with the 0.7 down here, okay, or 0, and then go up in 0.2s. Okay, so each box here is 0.02. All right, each box here, we've got 60 to 20 is 2. All right, so be careful. Just check those boxes before you do anything else. Okay, plot your data. And being very, very careful to do so, okay, using big X's and noticing that they've deliberately chosen their axes so it takes up a big space. That's why we try and do that way so that you guys can read the data more clearly. Okay, I've drawn my best fit line. Okay, to be honest, usually when I draw these lines I do look again and go, am I happy with that? The way that I check is I look at the distribution of the points. I've got 1 above, 1 below. 1 just below, 1 just above. So I've got 2 above, 2 below. These guys are pretty much on the line. He's very close to the line, just above, he's just below. I've got 3 above, 3 below. I'm pretty happy with that. What's all this other gubbins? Well, you're told on the next question to calculate the gradient, but also to make it clear what which data points you're using to calculate that gradient. Okay, so you're actually invited to make it very easy. So I've identified 2 points. I've deliberately chosen these points because they're on the line. All right, they're on the line, but they're also on the grid lines. Notice I have not used any of the data points. Never, ever, ever use the data points. Use points on the line rather than any of the data, because they are not necessarily on that line. Okay, I've taken the coordinates and I've written those coordinates down here. So we've got 1.98 and then 1.1. This should be here, and then 90 and 166. copied those values into my calculation of the gradient. Okay, 166 minus 190, gives me 86.4. Before we move on from this, one small point, notice I have not forced my line through the origin. Okay, it doesn't need to go to the origin because this is not the origin, right? This is not 0, 0. All right, we don't need it to always go through the origin. Don't force it. Okay, back to question C. We then take my data. We calculate the value for acceleration g using the value of my gradient divided by 8.7. Don't worry about where that 8.7 comes from. You just have to use it. 9.93. Again, a check. Well, do I know g? Yes. G for you guys is 10. So you guys, if you're getting 9.93, that means a 99.3% accuracy. That is very, very, very good. Okay, that means that your line has been drawn well. It probably means you're going to get all of the marks for this paper, for this particular question, because all of that has been leading to that. It's what's called a quality mark. Okay, so always check if it's something that you know that you're comparing it to, then it's highly likely that your number should be similar to that. Now, obviously, it could be the case they've designed the question so that it's not the same. I would doubt that. I've never ever seen that happen before. However, you never know. I would imagine that would be followed up in here. In this question, it says another student says a more accurate value of g would be obtained if the value was timed over great distances. Wisely correct. Well, we've had this before because when we're timing using a stopwatch, we have human reaction time. Okay. Human reaction time would be relatively smaller. It wouldn't be smaller, but it'd be relative. If I'm measuring something, my human reaction time is 0.2 seconds. If I'm measuring 20 seconds, well, 0.2 divided by my 20 would give me 1%. I was short 2%. However, if I measure something, same reaction time, let's just take an exaggerated example of 200 seconds, then that suddenly becomes 0.1%. Okay? The relative proportion of those numbers is going down by measuring something which is longer. Alright? So like I say, you should expect this number to be close to g. If it's somewhere really, really far away, check your data again, or check the next question. Alright? If it says, you may notice that your value is not very close to the value of g equal to 10, comment why, then you've got to think about what's wrong with the experiment. However, I think that's a difficult question at this level. I would go for hoping that your data is going to be correct.